Hello, today we're going to talk about the Witting reaction. So the pronunciation here is a V. And we'll also have another word that's a little unusual pronunciation with this reaction, and it's called an illid. So this is reactions 9 and 10 kind of combined from the chapter 18 reaction list. And what I'm going to do first is show you actually reaction 10 overview so you can see what the overall reaction is here. So there'll be some sort of carbonyl. And these could be both H's. So the R will either be an H or a carbon group. So it could be formaldehyde technically, it could be an aldehyde, it could be a ketone. And this will be reacted with an illid. And an illid reagent is going to be triphenylphosphine. So it's phosphorus with 3 phenyl groups on it. So this part of the molecule is called a triphenylphosphine, but that's not the whole molecule. And then this will have a carbon, and that carbon will have 2 groups on it. And here the R double prime and the R triple prime. Again, these could be hydrogen or a carbon group. Okay, and what effectively happens in this reaction is that the carbon-oxygen bond on the aldehyde or ketone gets broken, and the carbon-phosphorus bond on the illid gets broken. And what happens is that this part of the molecule on the right, the illid, and this part of the molecule on the left end up together. Now that can happen either in one of 2 ways. You can have them connect as they look here in this picture. So that would be R triple prime, R double prime, and then on the other side, you'll have the R prime and the R, or you'll get the other stereoisomer. Now, it is possible that some of these products might not be stereoisomeric, so swapping the groups might not actually give you a unique compound. And it's also true that one of these might be more stable than the other. So recall your alkene stability rules. And that is that the trans tends to be more stable than the cis, which is sort of a very specific example, but basically we're going to, if there's a difference here, we're going to favor the less sterically hindered alkene. So just as an example of this reaction, one that we do in the organic 2 labs sometimes, but we are not doing this current semester, is synthesis of trans stilbene. And transstilbene, you are probably familiar with because I believe we used this to brominate in our kind of classic addition reaction, addition to alkene reactions. So this is transstilbene. Cisstilbene, of course, let me swap that around. Would look like this, but this is going to be, you know, those phenyl groups are going to be bumping into each other. So this will be the favored, more stable product, and this will be the less stable minor product. In addition to that, the melting point for this is very low. I believe it is below room temperature. I would have to look it up to be sure. But because of that, it's going to be a liquid at room temperature. And so usually this is going to get cleaned out with our workup of the reaction, even though it's probably already the minor product. So with this reaction, we really end up with a lot more of the transstilbene, or basically solely the transstilbene, both because it's the major product, but also because that cisstilbene is very easily cleaned up. So this reaction, the way it works is you would take benzaldehyde, which some of you had for your unknown earlier in the semester, and you know that smells like almonds or cherries. It has kind of a sweet smell. Most people think it's a pleasant smell, but everybody's got different tastes on that. And then the illid that we use is the triphenylphosphonium chloride. Let's see, so it'll be the PPH3. And we have the carbon here, and that's going to have one phenyl group, and a hydrogen. Okay, and so we can see how, you know, taking these two parts of the molecule and putting them together one way gets us the cis product, and putting them together the other way gets us the trans product. It turns out that the byproduct is going to be effectively the other parts put together. So it's sort of like a square dance where the two parts of the molecule sort of change partners. So that'll be the byproduct of this reaction. And this one is pretty bulky. So if we think about this reaction, it's not very what we call atom economical. Atom economical is when we look at, atom economy is when we look at how many of the atoms that we put into the whole reaction end up in the actual product. And so here, especially with all those phenyl groups, this one is not a very atom economical reaction. However, one advantage to it, a pretty big pro on this one, is that we can control the exact location of the double bond. Whereas with our other way of making alkenes, it can be sometimes a little harder to control where the double bond goes, and then we also still have the regiochemistry issue. So kind of an alternative to the Wittig would be elimination, and a con for elimination is that we basically it's harder to control the location of the pi bond that's formed. A con for this one here is poor atom economy. And I do think this reaction can be made to work quite well. However, the reaction we were doing in the teaching labs just works okay because it uses a weaker base to make the ylide and just doesn't work all that well. Okay, so next I'm going to go into the making of the ylide and then the mechanism of the Witting reaction. So this is one where I'm not going to ask you to draw the mechanism for this reaction, and especially once you have the ylide, it's kind of easy to think of these as like, you know, Legos you're taking apart. So, you know, here you're taking these two pieces and you're putting them together, and then you're taking the other pieces here and here and putting those together. But you probably will want to know the kind of general process for the synthesis of the ylide. It's not too hard, but it might, it'd be good to practice it just a little bit at least. Again, I'm not going to ask you to draw it, but it might be helpful for you in working through the process. So the synthesis of ylide is reaction 9. And here you're going to take some sort of Rx, where of course X is going to be some sort of good leaving group. It might be an actual halogen, but it could be a sulfonate, like a tosylate, mesylate, or triflate. And then here, the R here, we really need this to be primary or secondary. Main reason is, I suppose it could also be methyl, but it really needs to not be tertiary, because we need at least one hydrogen atom on here. And also, we're trying to make this go SN2, and to make it go SN2, we really need it to be less substituted. So because we need one hydrogen atom that we're going to remove, plus want SN2. Okay. So let's do an example here. Oh, sorry. Let me write down the reagents. The first reagent will be triphenylphosphine. And then the next reagent will be a strong base of some sort. So this could be amide, LDA, hydride. Technically, it could be one of the alkyl lithiums. It could potentially be an alkoxide or a hydroxide, but it does need to be a pretty strong base. All right, so we're going to start out with this here, and I'm going to put in the PPH3, and we're going to use butyl lithium for the very, very strong base that we're going to use on this one. And again, this is called triphenylphosphine. And phosphines tend to have pretty strong odors. They also kind of kill your nasal passages. So I never had to use these in grad school, but some of my lab mates did. And they did not have such a great sense of smell after all of that. So notice we have a secondary carbon here. And we do have an H present, so this is going to work fine here. So the triphenylphosphine will come in, and we're actually going to do, for the first step here, this is going to be an SN2 reaction. So the phosphorus will attack at the alpha carbon, and the halide leaves. All that happens simultaneously. So now we have a phosphorus carbon bond, and that carbon still has those two methyls on it and a hydrogen. and then there are the 3 phosphoruses on that triphenylphosphine. So when we've done this, the phosphorus now has 4 bonds to it. So that's going to have a positive 1 charge. And of course, we've got bromide anion as our leaving group. All right, next we're going to put in our very strong base, which here is tert-butyl lithium. So we're going to have 1, 2, 3, 4 carbon atoms. And I'm going to just go ahead and draw it as a bond line drawing of just the carbanion here. The lithium, of course, would be the counter ion. Okay, so this is going to act as a base. We're going to take the proton from that carbon. Lone pair will go to the carbon. So this will just be a proton transfer. Okay, so now we have this zwitterion, ylid, and zwitterion is when you have a positive and a negative charge in the same molecule. However, we can draw a resonance structure for this since phosphorus can exceed the octet. It's in that 3p block, and we can do a double bond like this. And this is kind of how I prefer to draw the ylid, because I think it makes it easier. I'm so sorry. I think I just changed the groups here. Sorry about that. Those were both methyl groups, and somehow I magically converted them to hydrogen. So let's fix that. Okay, so this is easy to see that basically once we do our Wittig reaction, it's going to be this carbon double bonded to the other carbon in the aldehyde or ketone, and then we're going to have those 2 methyl groups on the one of the vinylic carbon atoms. Okay, and since this is a symmetric group that we're putting on here, they're both methyl groups, that means our product is going to be non-stereoisomeric, because even if we swap these 2 groups, you'd still have the same molecule, so we don't really need to worry about that. So a lot of times you'll be given the ylid in this form, or asked to draw it in that form, and if that works for you, it's totally fine to do it that way, but if it's easier for you to see it in another way, then that is totally fine as well. Okay, so let's take this ylid that we just made, and we'll go ahead and do a Wittig reaction with it, and I'm going to show you the mechanism. Again, I'm not going to ask you to draw the mechanism for this one on any sort of evaluation or examination, but I'm going to show you how it works. It's kind of weird, and then you'll know how it works. But for these, I'm really going to be looking for you to just draw the correct products. All right, so the ylid that we made in the last step was this dimethyl. Okay, and we're going to draw the mechanism for this. All right, so let's do butyraldehyde. 1, 2, 3, 4. Okay, and we can go ahead and draw the products for this, or the product in this situation. It's going to be these 2 groups added together, and we're going to make a new carbon-carbon bond. Okay, and then this will be the byproduct that we would have to clean out. Okay, so let's look at the mechanism of this. To draw the mechanism, the other version, the zwitterion version of the illid is the better version to use. So I'm going to draw that instead. Oh, there I go, drawing it the other way. All right, so this phosphorus will have a +1 charge. This carbon will have that negative charge. And so this is going to be, you know, this carbon is nucleophilic because of that negative or partial negative charge. And that's going to be the nucleophile that's going to attack the carbonyl carbon. So this will be nucleophilic addition, just like we've been doing all chapter. And I'm going to kind of draw this in a slightly different orientation than I attacked it, just because I need to set it up for the next step. And here's where, again, if it's helpful for you to draw things in a different color to kind of track everything, that's totally fine. And it might be helpful, so let's do that. All right, so the new bond that we just made will be this bond right here. And then I have this carbon here, and it's going to have those 2 methyl groups on it. And then it's still attached to the triphenylphosphine group. Okay, and then of course this oxygen now has a -1 charge, and that's going to attack the phosphorus here. So this will just be a coordination step. So we now have this new bond between the phosphorus and the oxygen. And now what's going to happen is this is going to kind of collapse, basically. I would call this probably an elimination step because we're making new pi bonds. But it is kind of a strange one, to say the least. I'm putting a question mark here, but that's kind of how I would define it. So what's going to happen is two of the electrons will go to make a new phosphorus-oxygen double bond, and then the other 2 will go to make the new carbon-carbon double bond. And so now we're going to end up with that's the new bond there, the new double bond. And then this carbon has the 2 methyls on it. And then, of course, we end up with the triphenylphosphine oxide as the byproduct. And that is the Witting mechanism. This particular one is not stereoisomeric, because I could swap either side and I would end up with the same exact molecule. I did want to just point out one reason kind of why this happens or how it can happen, because even though, you know, we can draw another resonance structure for carbonyl bonds where we put a positive charge on the carbon, and then a negative charge on the oxygen, we tend to not see as much reactivity like with the oxygen having a negative charge and the carbon having a positive charge. And that bond is pretty strong, or very strong. And so the reason for that is the carbon-oxygen bond. If we're looking at the pi bond, these are both going to be 2p orbitals that are involved in the pi bond. All right, 2p and a 2p. And so here you have a good size match, and that increases overlap, and it makes that carbon-oxygen double bond stronger. Whereas if we are looking at a carbon-phosphorus double bond, we still have a 2p, of course, on the carbon atom. But if we're looking at the phosphorus, that's going to be a 3p orbital. And so here we end up with a pretty significant size mismatch. And so that's going to weaken the carbon-phosphorus pi bond. And so that's part of why this reaction can happen. And don't forget that you can use these ylids as nucleophiles for the conjugate addition reaction as well. That was one of the ones on our list. All right, thanks guys. Let me know if you have any questions about it.